difference between distance and displacement. Distance is a scalar, displacement is a vector. Distance has magnitude only, displacement has magnitude and direction. Okay, size and direction. Now, part B, we've got a distance time graph. Okay, so you've got a train journey, and let's read the question. Shows an idealized displacement time graph for a journey of a train along a straight horizontal track. So it's the movement is sideways. Okay, from the moment when it passes a point A on the track, initially the train moves in an easterly direction. Okay, so what I've done, as soon as it says easterly direction, I've just drawn the compass north, east, south, west, so I can get my bearings right. Okay, so it moved, let's say, that way. Okay, easterly direction. So let's say it's moving right, just for argument's sake. Okay, so what we've got is that for the first 4 seconds, it moves to 600 meters from A. So if this is A, so let me say that is A, that's your starting point. You move easterly that way, 600 meters that way. Okay, that's for the first 4 seconds. So from there to there, you've got to 600 meters. So you move from there 600 meters to the easterly direction. Okay, then from 4 seconds, sorry, not for 4 seconds, 4 minutes to around about 6.7 minutes, you go from 600 meters from A back down to zero. So back down your starting point. Okay, so that's your displacement. So you went from 600 first 4 minutes to 600 meters. Then after two and 2/3 minutes, you come back to the starting point here. Then you've gone a negative displacement. Okay, so negative displacement means in the opposite direction to where you were originally going. So it's gone 300 meters in the opposite direction. So that is in a westerly direction. So what's happened is this journey goes easterly 600 meters back to the start to then go westerly in end up in a negative displacement. So it goes 600 meters easterly and then 900 meters westerly. So describe the position of the train relative to A at the end of the 8 minutes covered. So at the end of the 8 minutes covered, we realize, oh, okay, it's a minus 300 meters displacement. So it is what? 300 meters from the starting position. Okay. And that minus represents is the opposite from which way it was going before. We know it's going east first, so now it's west. So it is west of the starting point. Okay, so west of the starting point. Starting point is that way. There was just, let's say that was starting point going that way, west. Okay, so 1 mark for saying 300 meters west of A for the second mark. Right. Now it says use the grid figure 2 to plot a velocity time graph of the journey shown in figure 1. Okay, velocity time. How do we go from a distance time to a velocity time? So we know that the velocity is actually the gradient of a distance time graph or displacement time graph. So we know that the straight line here on a distance displacement time graph gives us velocity, and a straight line is constant gradient, so that would represent a constant velocity. So the velocity stays the same for the first 4 minutes. This is now key for calculation. Now, how do we work out the gradient for this section here? I've called it A. It's the rise, which is 600 meters, divided by the run. Now that has to be in seconds. So it's 4 minutes, 4 times 60, 240 seconds. So it's the rise, which is 600, over the run, which is 240. That gives us 2.5 meters per second. It's a positive gradient, so that should be a positive value. So I've done 6 take away 0, final, initial, divided by time taken, and 2.5. This is the next section. It is another straight line. So from here to here, there is a negative velocity. Okay, so section, I've called it section A. I'm gonna actually change that. I'm gonna call it X and Y because I don't want to confuse it for the starting point A. So I'm gonna call that X, call that Y. Okay, that's X and Y. Okay, so it's the rise over the run again for the second section. Okay, so its final displacement is minus 300. Take away initial displacement, which is 600. The net displacement from there to there is minus, so you start off at 600 to get to minus 300, 600 meters to get to this position. You have gone negative, gone to left, so it's negative 900 meters over 240, because it's again from 4 minutes to 8 minutes, so it's 240 seconds, and we get minus 3.75 meters per second. So this part of the journey is a positive speed going that way. This part of the journey is a negative speed, which is going that way, minus 3.75. So we know it's constant speed there, constant speed there. So the first 4 minutes, we know that you have a constant speed of 2.5 meters per second. Constant speed, so that's a horizontal line. And then the second part of the journey, we know it's another constant speed. It was a constant gradient here of minus 3.75 meters per second, and that works out with my scale as well. And I know what happens is that the journey, you have 2.5 meters per second constant speed for 4 minutes. The object turns around, goes the opposite way, and that would signify a negative speed. And that change here on the graph was instantaneous. So that it didn't take time for them to, and you can see that because it is a defined point, the gradient went from that to that instantaneously at 4 minutes. Okay, so we have to do the same. So the speed went from 2.5 meters per second to 3.75 minus 3.75 meters per second instantaneously, same time. So that's where we connect those two lines. You got 1 mark for selecting a correct scale. You had 1 mark for calculating the speeds correctly. Sorry, 1 mark for calculating the speeds correctly, and then drawing this line, that's the 3rd mark, and then the 4th mark is that line there and connecting them up. Okay, so that there is the 4 marks for that last section.